Okay, so good morning, everyone. Thank you for coming to this weekly colloquium of the IAC. Today we have with us Almudena Prieto, which you have probably already heard of. So she has been around for a few years now as the PI of Parsec, and right now, today the talk that she is going to give to us is about the first adaptive optics instrument for GTC, which is FRIDA, for which she is the PI. So without further ado, the floor is yours.
Thank you for being here. Yeah, I'm going to talk about adaptive optics. Yeah, it's okay. It's okay. Yeah. I'm going to talk about adaptive optics and GTC associated with the scientific instrument that is FRIDA, and I will try to make highlight what are the capabilities of FRIDA that are unique, and drive or propose science cases that make profit of these unique capabilities. So to introduce FRIDA first, is the first scientific instrument that will deliver images and 3D spectroscopy integral units at the diffraction limit of the GTC. And the diffraction limit of the GTC implies that we are going to get to angular resolutions that are a few tens of milliseconds. And to get this resolution, which I put it here, from 40 milliseconds in the K band to factor 2 less in the J band, means that we had to correct the atmosphere with the same we cannot get this resolution. If we achieve these resolutions, if we compare with a normal scene condition that we can get in the infrared, the median value of 0.5 seconds, 500 milliseconds, or 600 milliseconds, these resolutions imply a factor of 10 superior, okay, with respect to normal scene conditions. In collecting power, it goes quadratic, it's a factor of 100. That is what it implies to switch to high angular resolution here in GTC. To achieve that, we need to use something which is our adaptive optic module that we have developing here at the Institute. And this is so-called GTCAO. And so FRIDA will be the scientific instrument, and GTCAO is the module that will correct the atmosphere, will remove this synth and achieve these diffraction limits. And in the saga altogether, we had to join as well in this club of GTCAO and the scientific instrument. We had to put together the telescope itself. The telescope itself has to get a better or optimal performance, if you want, to accommodate the requirements that using an instrument as FRIDA or another scientific instrument that is going to work at the diffraction limit of the GTC. So it has to work to improve even better the performance of the telescope to deliver altogether the diffraction. That's what we aim on. So we have to coordinate very well together the scientific instrument, the adaptive of this instrument, this is another instrument, so and the GTC. And so when we put together all that, we can achieve these resolutions, but sometimes we might get in trouble. We will be a family that will try to be in harmony, but not always it's going to be like that. But still, even if we do not achieve the diffraction limit, even if it's not a factor of 10 or higher angular resolution, you can get what we call scene reduced. So you can get maybe a factor of 6, 5, it's already an improvement. That's one to say. So diffraction limit is the goal, we go for it. It depends on your target as well, of the conditions in the atmosphere, but even if you don't achieve it, you gain. Okay, you can gain not factor 10, but you can get factor 5 or 3, depends. You always win. Okay, no, the money. So, what is FRIDA? Specifically, it will work in the infrared, near infrared from 0.9 to 0.5 magnitude is the range where the community knows how to correct the atmosphere and use this adaptive optics system. And I put in red the things that are specific or unique in FRIDA as compared with instruments that are in the market. Or now things have big telescope now are the second generation instrument. They are more using other some of the capabilities here, but in general, the instruments that are on the market on the big telescopes with use adaptive optics either are a camera or an integral unit. And in FRIDA, we have both. And that is very important because the camera will allow us to get a faster acquisition of our target, which will be faint, and we'll have to put it in the integral unit, and the integral unit that will work on adaptive will be very small field of view, okay? So this will make our acquisition very fast and observations very fast as well. Because we achieved or wanted to achieve the diffraction limit, we wanted to sample the diffraction limit correctly. And then we have these small pixel scales that need sampling the whole infrared, the whole near infrared. When I say infrared, I refer almost to 1 to 2.5. So these are 10 and 20 milliseconds. What happened in the market in general is that they have a fixed pixel scale. Sometimes they sample the pixel scale, need to sample the whole infrared range. Usually it's not the case, it's a compromise. It's very important to need to sample the diffraction limit, because if you don't use that, if your pixel is much larger than the diffraction limit, you lose your resolution. You know, okay? For example, what is happening now with GWC, the infrared is no liquid sampling the near infrared. So the resolution it can reach cannot profit properly. We do important. Field of view are small, are from half a second with the integral unit to 1 second. In the imaging camera, it's larger, we will have 40 seconds. And field of view, the spectra, we also need to sample spectrally, okay? So we have a spectral solution, and then we sample the spectra such that we need to sample all, not only spatially, but spectrum. And we have 3 spectral resolutions as well. This is the standard one for active optics and integral unit. This one, 150 will allow us to cover the whole range, spectral range from 1 to 2 microns. This is unique for an active instrument. And people in stellar astrophysics will enormously benefit. Unique in stellar in adaptive optics with an IQ. And yes, now the price is quite a bargain. It's not for sale, but this is what it costs. Original, including the detector. Okay, let me go briefly of what implies to have to get to this status we have now. We started with the call of in 2000 the GTC made for first light instrumentation, and there we were with first instrument that there was a proposal that was Atlantis. The proposal failed because Atlantis was exactly the same, and a camera and integral unit working at adaptive optics. It could not be done at that time because there were no funding at GTC to do the module, the adaptive optics module, and this is a part that has to be developed by GTC. So in 2004, I was contacted by GTC then to say, okay, now make a proposal, make a formal proposal, and we will build an instrument that will accommodate for the adaptive optics module. We have funding, we will go together. Okay, and so it was created this consortium, and it was no time, no way to develop the instrument FRIDA that is came at this time at this institute because it was completely caught by Emile and Lucid. So what it was decided is that the instrument is going to be built by the three partners of GTC, University of Florida, the University of Mexico, and this institute. Okay.
I see we start before the Big Bang.
Eh? Yes, because we are pioneers. Exactly. So in 2006 we signed the contract finally, but now we are in the line of the universe. That is the point down. Okay, and so GTC round of funding with the development of GTCO was stopped in 2012, and in addition, because GTCO was stopped, FRIDA doesn't make any sense to have a module for a correction. The detector was also taken away from us. It was bought by the GTC. So no detector on GTCO, you could imagine, was quite frustrating. But then in 2015, with the effort of the institute, in particular with the director Rafael, there was funding from the Gobierno de Canarias that came to our rescue, and so GTCO came online, came back. And then we also, GTC should have asked for funding to build, or give us a detector. It was not doing that. So we had to look for funding. We got so many proposals to get into funding for a new detector. It's very expensive, $1 million. But finally, the government has come again to our rescue, and it was going to finance a detector. So we were on track, and by last year, we are complete. So FRIDA is complete, and GTCO is complete. GTCO no one is complete. It's a telescope. It's operating. It's attached to a scientific camera, which is Grand Prix, and is producing now very good images. So it's commissioned. This camera Grand Prix will be used to commission GTCO and the telescope. So all is in track, and now we are a bit on the line of GTC as well. The telescope, I say, has to get a maximum performance in operation mode to adapt to the requirements that GTCO and scientific instrument demands to work with to get diffraction limit. So this is how is the situation now. So we are basically done. Who is in the market and with their own instruments and good resolutions. Many telescopes, most telescopes, the big telescopes in the world have are already in the second generation of instruments. We are going to come here in this line, and with them, they are going to join the club. And what the message I want to say is that we are still very competitive. That's why I want to highlight the unique capabilities of FRIDA. We are very competitive with all of them because of the characteristics I mentioned before. Okay, compared with the space telescope, yes, I wanted to say that compared with the space telescope, we have a factor 4 better angular resolution, both will be a little. And with the general speed is 60% better in angular resolution. Okay, so this is what we are getting, and we're having a big telescope, and a big telescope that goes with the diameter and then also with the angular resolution, with the wavelength that we have. Okay. So energy concentration works with a power of 4 because of course to reduce, you try in a point, so you have to concentrate the light in the PSF according to your resolution, but also you reduce the background the same way. So all work with power of 2, and then together is a power of 3. That is what it does. Compare with the space instruments that we have now that can operate in the near-infrared. So now I want to emphasize a little bit what is the difference to work with angular resolution, this very high angular resolution, and to work with lower, very low resolution. Okay, in the case of milliseconds range, when you switch to AO or to any other system, it could be other wavelength range in the electromagnetic spectrum, or to work with a standard low resolution. So I took this galaxy as an example, and I will focus only in the center of the galaxy, and I will show you a difference of what is the center of the galaxy look like when you use a program like SYNC. This is an image of the center of the galaxy, same field of view, and taken with the satellite guides. You have to go to the space to get ultraviolet. So you see the center, the nucleus of the galaxy, and a kind of nebulosity, maybe some blobs here. When the same field of view, you switch to the space telescope. In the UV, it has much higher resolution. This is 50 centimeters. This is 2.5 meters. Okay, this is what it has. You have a nucleus of the galaxy, and all this diffuse structure, it has split in many sources. These are star clusters. Okay, hundreds of them. This is the difference of looking in this way or looking in this way. We have other counterparts improvements to do this, but for the center of the galaxy is quite complex. If you look in infrared, which is the range we are talking now, you have this same by cursor and spacer. This is the center of the galaxy, the same figure. And here you have this ring, white dark, and then you switch now to adaptive optics, and then you see again the nucleus of the galaxy, and again all this region is split in many sources. Here. This is what it makes to switch to this angular resolution. What is the counter? What is the drawback here? That this into an angular resolution, adaptive optics requires a bright star in a We can do this because the target, the nucleus, is very bright, so I can use it to correct our speed. But I cannot use it anywhere else. That's the difference. With low resolution, this telescope gets the whole galaxy. A low resolution, but the whole galaxy. With this angular resolution, I can get only where my target is close, relatively close to a bright star, because I need that bright star to correct them. That is the drawback. We had to find ways to compensate it, but that is the main difference to work with these low resolutions or to switch on to very high angular resolution. It's not all possible. So let me go to now specific science cases that we can address with FRIDA. Don't compare with resolution, simply compare with other instruments in the market and what additional characteristics or what additional science we can do with it. Okay, so I will concentrate with stellar astrophysics or Milky Way, and I will say that FRIDA will get big advantage if we go with the infrared unit, and of course the highest spectral resolution that we have in the industry. So, and I use always this example because it's very nice. This is an image, a spectra taken with adaptive optic instrument. It's called Price at ISO, and it's a binary system and very close and very bright. It was start. This is the spectra of each of the two companions or the two components of the binary system. And it's done with Price, which has shared spectrum operating in adaptive optics. So it's got much higher spectral resolution than we have. It's a factor to higher. They have 100,000. We are 10 kilometers per second. They get down to 3 kilometers per second, even less than 3 kilometers per second. So the quality of the spectra in the infrared is only the K-band here, something around the K-band. Well, it speaks by itself, polar lines. And they could do that. They do that with a long slit, okay? Because Price is a long slit spectrum. It's not an L. And that is what will make the difference for us. So I will go on it, but when you have a long slit, and you want to put your target on the slate, you have to open your slate. You cannot sample your slate comparable to the angular solution you are going to achieve. And that is the point here. They open the slate to get more photons. Otherwise, if you reduce to the angular solution that you achieve, or you want to put something even getting smaller, you are going to lose photons. So you have to go with very bright photons. So what they did is, this group of people is that they monitor one of the companions and sequentially in time, because it's variable, and because the resolution they have along the slit, they could sample the surface of the star. Okay. So they reconstruct the atmosphere, the surface of the star. These are different reconstructions from the spectra I showed to you, taken at different times, separated by 1 hour or less. And on the slit, they have the variation of the spectra independent, spatially resolved across the surface of the star. Okay. And so we reconstruct the atmosphere. So in a way, you could think of even doing weather forecast in stars. So what is the special with FRIDA? How can we compare? What can we do in that respect with that? Well, we don't have the spectral resolution. It's one, as I said, it's 1/3 lower, but still is very high. But we have much superior angular resolution because we don't have a long slit. We don't have to close or open any slit. Our integral unit takes the whole photons of the star. That's the advantage. And so we profit of the angular resolution, and we have all the photons of the star in our field of view, in our integral unit. And because we increase the angular resolution, of course, we have better sensitivity. In this case, it's a factor of 10 because it's much, because it is, well, the difference in telescope size is not that big, between 8 meters and 10 meters. But the problem is that they have to open the slit to get photons. We don't have to open anything. We keep our liquid sampling of the PSC, our small pixel scale. In this case, will be open meters. That will be the resolution. Our pixel scale will be 20. So we don't lose sensitivity. We reduce the background in our star because we get less pixels below our point source, and we increase resolution. Okay, what it means? It means that we can get much further in the galaxy. I'm doing this simple exercise. We don't have to get very close to stars, and they don't have to be so bright. We can get faint. There is a limit, of course, because this is a very high demand exercise. You are 10 kilometers per second, but you have bright stars to do. So we can do the exercise with less constraints and weakness of distance. And so, besides not doing this atmosphere mapping of stars, or we can study structures around the star. We can see the accretion. In a structure in the accretion, we can map the surface of the star. We can map the structures around the stars, and so the accretion is very high. And we can identify sources in our accretion disk, potential planets, or study the substructure of winds, the origin of the winds of the star, mass loss. All that we can, in a spectroscopy, we can study the detail. So I want to jump now to outside the galaxy and go to the local universe. And now, in that case, what we are going again to profit a lot in the local universe is again with the integral unit and our angular resolution. And local universe, I will take a particular target, which is Andromeda. Because it's our closest, it's our nearest. And Andromeda, one passing in Andromeda implies all these milliseconds, 270 years. But our angular resolution is factor of 10 high, at least. So what I mean is that I can see subparsec Andromeda. I can study subparticle structures on Andromeda. And I can do it spectroscopically with the infrared beam. So I think this is a super target to go in such a detail, enormous detail, and discovering the physics of this structure. No? We can go not only the center, we can go the disk, we can study at this scale the spiral arms, the halo, all we can do a subparticle scale. And in fact, a 10th particle scale because of the resolution. Now, as I said at the beginning, adaptive optics requires a bright star to correct the atmosphere. And I said at the beginning, when I go to a galaxy, usually I have to reduce my work to the center of the galaxy because it's the bright point when it's bright. But Andromeda is fantastic because it's so bright. There are plenty of stars that can use for the adaptive optics coverage. Plenty across the whole body. So you see here the shape of the galaxy in a star. This is a collection of 2,000 stars I put here. You see them separately. There is no that plenty. That cope with the requirements we need for error correction. And of course, at the distance of any position in the target, because there are plenty of them. So basically, many of the structures or regions that you want to study, you will find something bright to correct the atmosphere. So any point you can study Andromeda at subparticle scale. Okay. So it's what to show you here, how we reproduce, how convince you that you can go any place on it by using any of these stars, bright stars, to correct the atmosphere. And this means that having this possibility in doing at this scale, we start to see things that are comparable, or we can get physics that it can be compared quite close to what we know in our own Milky Way. So I put here some applications, some examples of things that one can do. I have been working for a while on thinking of a survey or Andromeda. We are in the time of surveys. Surveys are done with all telescopes now, that mostly in imaging. That will be a survey, and usually a field, and that big field you want to get many times. Here there's only one planet. Perhaps one of the most important ones we have in the universe is Andromeda. The survey of one, but complete the galaxy. So any point we can access, so we can do a survey of that covering the galaxy. We can go to dynamics. We have very high spectral resolution. We can do it. We have the ability to get down to this 10 kilometers per second and get with the spectrum. And so we can get a direct estimate of the mass. We can study the globular cluster population. There are hundreds of them. These globular clusters, are all systems. They are very good traces of the formation, of the origin of the galaxy. They tell us a lot of information on how the galaxy has been formed. So we can get, because we get to these velocities and distortions in our kinematics, and maybe distinguish dark matter distribution in the galaxy. And of course, the red supergiants are basically, most of these ones are very bright, and per se are targets, because red supergiants and giants tell us about the age of the time where a given structure is formed, where they are located, so we can have where the spirals are formed of the disk of the bulk simply by following or finding red supergiants and getting the spectrum. And of course, we can do something like it's done in our galaxy. We can do proper motions, orbit stars, and in particular, we can do it around the black hole. And it's interesting to know that to say that the center of the Andromeda is a bit different from ours. In the center, there are 3 nuclei, no one. Maybe it's not so peculiar. We see 3 nuclei because it's very close. maybe many other galaxies have several nuclei. Well, okay, we can do proper motions for stars in Andromeda because we go at these scales. Okay, and so I jump now to high redshift. High redshift is more complicated. We need collecting power, we have a big telescope, and we need angular resolution as well, because we know that what we are seeing now at high redshift are quite point-like sources. Maybe because what we get the brightest point could be. But that is what we have here is an emission. Now generally stick is our telescope in fashion. And the sources that are found at high redshift are very point-like. So angular resolution makes our role because it's easier to concentrate the light, but if we have angular resolution, we might be able to see where this point source, where is the host of this point source, what is the, if they have a standard structure, where is the galaxy which is behind this galaxy, the structure. So the sources are small, our integral unit is small in field of view enough to cover any of these sources. We have the angular resolution and to study the source itself in spectroscopy with the IQ, to characterize the source, to distinguish how are they. This is what is being doing now with the younger speed, okay? So I'm not saying nothing new, they can do it, but what I want to emphasize that we can do at least as competitive or even better for two reasons. Because they don't equal something the angular resolution they have. Our angular resolution a bit better, but not that much, but it's better, 60%. But it's the non-equal something. So their pixel scale or the pixel scale is 100 milliseconds, but we go 40. Okay? So if there is a point source and we integrate on one of these sources, we might see perhaps the structure behind. So we have the chance to do it. And the other problem they have, or the other problem, it's a compromise of things that you want to do when you make the science. They have a spectral resolution which is relatively low, even for normal instrumentation we have on the ground is 200 kilometers per second. We get much higher, and therefore we can afford this spectral resolution. And the good thing of having higher spectral resolution when you can afford it, and it's true that the sources are faint, so you might want to integrate things. But when you go to point sources and you concentrate the light into PSF, you might be able to get a much finer spectral resolution. And this resolution will allow you to blend these vision lines for social will be difficult, but vision lines that you have in the spectrum. Something that is a problem for them, for the younger speed now. There are lines that even the typical lines that we are used to seeing in the optical, they cannot be blended. They are together. But we can do it. We can do it because we have it. They cannot. They can't be at best. Most of the spectra are now available in universities with a prism, which is even worse for the solution. They want to get the whole spectrum beautiful with the redshift 8 or 9 and full of lines there, but blended. So that allows us to get a bit more on the morphology of the source, and even mass, if we have a certain spatial extension with these cinematics, we can maybe measure close mass. So it's possibilities. Okay. Again, none of the sources in principle we can do it, the ones I showed before, because we need a bright stars, okay, for the operators. That is the point. So I always have been passing the message to the community that the survey of fields with a bright star, a deep field, with a bright star in the field, not necessarily it has to be in the center, but somewhere less, would be an access for us, because you will have a bright star in the field, you will have a deep field with many sources, and you will immediately go to another instrument and study these sources are very fibrous. The ones that I showed before, we cannot do it because there is no brightness. But we can look for others. There are, and I have been doing a quite extensive search of targets high resolution and looking for bright stars. There's bright stars in this range. Okay, we have to go. We need below 70 magnitude around something that are high resolution. There are, and we have now relatively with sample of them. There are many more. It's something that I do when I have time to do it, or when I have people that could help me or help to look for resources. But these are samples of relatively high resolution sources. As a high resolution, I showed you before with university, I only get a resolution 3, and we found bright stars nest. There is the target of the star, the target, the star here, the target, and this is the same as the star because R is bright itself. These sources we can do right now. We can do now with graphite, whether we do commissioning, we can do it here. So we can integrate of that thing. We can integrate of the sources with a much bigger telescope and see what is the structure, where is the mass, where is the kinematics of this source. Okay, so we can do it, and there are high resolution, so it's just matter to look for them. And I finished. What I wanted to do, with these samples. FRIDA is done, so work done. GTC is done. As I say, the telescope is operating with graphite. That's an active camera assisted with the GTC that is operating and producing very nice images in the last weeks. And we have to GTC, the telescope itself, is working very hard to improve this performance to cope with the requirements that we have. So this, for the last 2 years, they have been working, they continue working, so it's work in progress. And I try to highlight that the Milky Way, we can do it at this spectral resolution, unique. And we can do in the near universe Andromeda, spectroscopically, any point in Andromeda, you can do it. A subparticle scale, 10 to parcel. And we can do the high universe, the high resolution universe. I will say, I want to claim we are going to do much better than university, as competitive as them, absolutely. Okay, that's a
Very much for this really insightful talk. So do we have questions in the audience first?
Thanks for the great talk, Almudena. And I have 2 questions. One of them I might have lost when you were giving the specs of FRIDA. What is the field of view of the IFU that you're...
half a second to 1 second.
Okay, so very tiny.
Very tiny.
Okay. And the other thing is that you were showing the Andromeda survey. I remember that Romano is also going to do an Andromeda survey, but the spectroscopy, the resolution is much worse than you have. Do you have an idea of how comparable things can be, and how you could, I don't know, maybe crazy idea, use Roman as, because it'll have the same spatial resolution as Hubble. The mirror is basically the same. So
this is the point. Is what I try to emphasize. Andromeda is not extensively with the star. What I want to say that we can do a 10th of parcel, any point, any point. And of course, with a very high spectral resolution, you need. And this spectral resolution is important because we are going to track stars. So we can really analyze the stars. And we can afford them because they are very bright. Yes, a wire Roman,
While Roman can have like a
but
larger view of things because they like two pointings, they'll cover the entire thing. You can select specific regions of things.
it's what I was trying to say at the beginning. When you don't switch to angular resolution, to higher resolution, you can do extensively, I don't know. Because we cannot do that. Because we always need a bright, always, even if we have the laser. So the thing is that with Andromeda specifically, we have the stars to do it. No, every point is not going to be an homogeneous order, but as you say, and I only put 2,000 stars, I mean, because I want you to see the stars individually. Many stars. But there will be other structures which are not good. Thanks.
More questions?
As the limitant of this instrument sometimes is that you have to have a bright star next to your target. Has been contemplated the possibility of having a laser guided star, or why is not would it improve the quality of this instrument, or was it contemplated to have laser guided star?
Yeah, the list is it's been done, been working, been developed. Yes, you are prepared for this. But now at first we go to natural, we need a star. With the laser, you need a star. What do you gain with the laser? A coverage of the star. Now I have to select, have to be specific in the selection of the star. But they need to have the service. With the laser too, but with the laser you can go with faith. Yes, so you sky coverage gets bigger. The quality with the laser is going to be the best performance is when you use a natural star to correct those. That's clear. And when you star is at the center with your own target, super. And then from there on, you get improvement, no necessarily that the fraction, but you can get very fast.
More questions?
With such high spatial resolution, the capability of FRIDA will be lost in many ways because you need a bright star. So is there no way that GTC can put a laser
It is
star?
yes, it's been built. It's in progress. The laser is being constructed.
It's in construction.
Yes.
So when will that come?
Well, we'll find it.
The scope in operation 2028. It will be in operation with FRIDA commission in 2028.
2028. All right.
We will get it. We will get over it. You know, the first music. No, now we can get only with natural light. But we will get it.
Okay.
Great. More questions?
What is the separation between the tip tilt star, the guide star, and the target that you the maximum separation that you have to have now?
Because we have an effect of the when the correction is put close to the target, and you have an effect in the atmosphere, it's called as isoplanetism. And as the atmosphere is not homogeneous for everywhere you put it. So you can correct that narrow pin, and then you get farther from that position, you are less good. Because atmosphere changes. It's very nasty.
Yeah, but do you have like more or less an idea of the?
Yes, I mean, half an minutes. It's
Okay,
about,
okay. To work about that, those of the.
yes, yes, yeah, well, that is the same, the governance program doesn't matter what which telescope.
Yeah.
Then she.
Yeah, 'cause I remember with Gemini, even with the laser, it was much closer. It was like I don't remember 30 arc seconds or something like that. It was teeny tiny, very hard to find the guide. Yeah, but thanks.
It's more about the here. I don't know why. Of course, the closer you are, here.
Great.
But I think this was related to the limitation in the atmosphere, or was most in the acquisition of the guide of the tip-tail star. That in the case of the Gemini, it was this problem of the atmosphere. So I think the isokinetic angle was very small or relatively small, or it was that it was a problem for the acquisition in the. Okay, you don't know. Do you know?
I think in Chile, the isokinetic angle is smaller because here we have more the turbulence is more concentrated. It's lower, and there is higher, and then the angle is smaller.
But I think, for example, in the cake, they have no problem to go to 1 minute. Yeah.
All right. So let me check if there are any other questions online. Second. Okay, since there are none, so we can thank the speaker again. And there should be a coffee break in a few minutes at the cafeteria. But before that, students, please come around so I can get for your attendance. Thank you.